Great. Okay, so yeah, let's talk about some data structures and algorithms. Data structures are a way to store data. Okay, there's different ways that data can be stored such that some things are beneficial. An algorithm, on the other hand, this is like a recipe. Like a recipe. Oh, God, why can't I spell? Recipe. What I mean by that is that, like a recipe, you have a certain list of ingredients, and then you have steps to follow. Step 1, step 2, step 3, step 4. And with these ingredients and following these steps, you get the result, which is whatever dish you have. So an algorithm takes an input and returns some output. Okay, you can think of an algorithm kind of like a program. You give it a certain input, the algorithm goes through some steps, and then it spits out a result. That's what an algorithm does. Okay, these are two separate things, and so don't confuse the two. A data structure is a way to store data. You talk about data structures. Is that what I want to say? No, I don't want to say that. Okay. The first type of data structure that we're going to talk about is an array. Okay. So an array is usually drawn like a rectangle with a bunch of cells. Okay, so this thing that I've drawn here, I'll refer to that as an array. And inside of the array is a certain number of cells, and this is the length of the array. So here, the length of this array is 1, 2, 3, 4, 5, 6, 7. Okay, that's the length. Arrays also have indexes, which is which cell it is that you're talking about. These, for reasons, begin with the number 0. Okay, so this would be index 0, index 1, index 2, index 3, 4, 5, and 6. This is just the what's the word? This is the convention that's used in computer science, okay, that things start with the number 0. If you don't like that, for whatever reason, you can write your indices like this: 1, 2, 3, 4, 5, 6, 7. I don't care. I would kind of prefer this just because I'm more used to it. But if you do this, I don't care, so long you're consistent. You can't start with 0 sometimes and then not other times, because that's just confusing. So you can use whatever indexing system you like, just to be consistent. And I prefer the top one. And that's what I'll be using during lecture. Okay. Now, inside of these cells, you can put basically anything you want. I mean, you could have numbers, you could have letters, you could have words, you could have Chinese characters, you could have an emoji, whatever. I mean, inside of a cell is whatever you want, but that occupies one cell. Oftentimes, you don't have it mixed like this. Arrays are either just numbers or just letters or, just one type of thing. But in any case, I mean, like there's no restrictions on the types of things that you can put inside of a cell. because, and you don't need to know how or why, but there is a way to map anything you want to ones and zeros, right? You don't need to know that, but basically, a cell is some sequence of ones and zeros, and how that's interpreted doesn't really matter. The point is that a cell can hold so many ones and zeros, and that's it. Okay. Actually, for now, I'd like you to forget a little bit about the ones and zeros. Think a little bit higher level for this discussion. Okay, so that's an array. An array has a length, and you can reference particular parts of the array via its index. Okay. A classic algorithm to start with is search. Okay. How do you find if something exists? So the way that this works here, because it's an algorithm, it has an input and an output. So here, input is going to be an array and an element. Okay, so you give an array and you give an element, and the question is, does this element exist in the array? And so the output is going to be, let's say, 1 if element in array or 0 otherwise. Okay. You could return the index instead. If it exists, you return the index. Otherwise, you return -1 or whatever. I mean, like, that's just sort of a detail. The point is that, here this is the algorithm has an input and it produces an output. Here it's a binary output of either a 1 or a 0. A 1 if this element exists, a 0 otherwise. Okay. I would like to pick on somebody just randomly. How about Vishruti?
Yes, hi.
Hey. So I'm going to give an array of numbers. Let's see, 3, 7, 2, 42, 18, 1. Okay, here's an array of numbers. And I want to know, does this array have the number 3? So first of all, like, what's the answer to this question?
Yes.
Perfect. All right. Now, how did you find the number 3?
By using the I'm not sure what's it called, but 0, 1, 2, 3. So it's in fourth array, I think.
Yeah. I'm imagining, you looked through the array and you saw the number 3, and that's why you said yes. Great. Now, one thing to know about computers is the way that a computer, or the way that an algorithm goes through this is, us, we have eyes. When you look at the array, you can see many numbers. You can see many cells in your same vision. But a computer looks at things like this, okay? So it can only see one thing at a time. That is, it can see one cell at a time. So what is the most straightforward or the dumbest thing that you could do to look for the number 3, for an algorithm to do?
Left to right.
Oh, I heard 2 people. Brian. Okay. Yeah. And Vishruti, what were you going to say?
So I was just going to say we would look at the fourth cell directly.
Why the fourth cell directly?
So we could see the number 3.
Yeah, this doesn't work because if you wanted to find the number 19, do you go, okay, so you go and you look at the fourth cell and the number 19 isn't there. So what do you do next?
Maybe look next to it.
Yeah, look next to it. And then if it's there, check to see if it's the number 19. If it's not, go to the next one, and on and on. So it's more like this, left to right. This is one way to do it. What's the easiest way for a computer to search? Start at the beginning and look. Is this equal to the number 3? No, it's not. Let me move to the next one over. Is this one equal to 3? No, it's not. Let me move over. Is this equal to 3? No, it's not. Let me move over. Is this equal to 3? Yes, it is equal to 3. So now I can return the number 4. But
A quick question. So it
yeah,
would just be in the sequence, right? Like we could use the either one. So 0, 1, 2, 3. So let's say if we're using that one, 3 equals to 3, the number we're looking for. So would it return the number or would it return the thing on top?
so I mean, really, it can return whatever you like, so long it's consistent. The way that I've written this is that it will return the number 1 if the thing is anywhere in the array, but you don't know where. Or if it doesn't find it, it will return the number 0.
Oh, okay.
But sure, I mean, you could change the output to output the index if you find it. And if you don't find it, maybe you return -1 because that's not a valid index.
Gotcha.
So, yeah, that's fine if you want to do that. Like the process is the same. It's just, yeah, changing the way that you want to have the output.
Perfect. Got it.
Okay, yeah. So use whichever one you like better. Okay. So, like a computer can't like look at many places at once. A computer has to do things step by step by step by step, and it can do that very quickly, which is why things seem to happen fast on a computer. But it could be doing some very dumb things again and again and again and again and again. It just can do those very quickly. Okay. So this, actually, I'll keep that. Look at the fourth cell directly. So this doesn't work. Because not a general strategy. So what I mean by a general strategy is that this algorithm, the search algorithm, should be able to take any array and any element and work. It should be able to find the element if it exists, or return that no, it does not exist. And so it doesn't matter how long the array is or what things are inside of it. It should work for all arrays and for any type of element. So this left to right, that does fit the bill. You start at the beginning, you look to see if that's it. If not, you go move 1 to the right, check to see if that's it. If not, you keep moving 1 to the right, 1 to the right, 1 to the right. And if you reach the end of the list and you haven't found it, then you can return no. Okay? So this is called a linear search. Okay, A linear search, yes.
I just have a quick question. So for the search algorithm, for example, if in just one algorithm, it also has the element three, such as like 3.1 something or 30 something. So when we use this search algorithm, what would the output be? Like there's no exactly number three, but like it has 3 point something like that. So it contains the element three. So what does the output be?
I see. So if you're looking for the number 3, but maybe there's no 3 exactly, but there's 3.1 or
Yeah.
something that's close to 3, then it depends. Like you can come up with different algorithms. You could come up this algorithm, this linear search algorithm, would return no. This would only find an exact match. If you wanted to find a rough match, then you would just, at each one of these arrows, like here, when you're looking at an element, instead of asking, is the number in this cell exactly equal to this number, it would be, is the number in this cell within this range of this number? And if yes, then you can return yes, otherwise you return no. But that would be a different search algorithm. You know, that would, I don't know, like a fuzzy search or something.
Okay, thanks.
Yeah. I'm just talking about the first kind. So this finds exactly the element if it exists. Otherwise, it returns 0. No, it doesn't exist. Okay. So that's a linear search. Now, a linear search, it can actually be a little bit broader than left to right. For example, you could go right to left. Same thing. I mean, you start at the end and then you keep going, looking for the element until you reach the beginning, and if you haven't found it, then you return no. That also works, but the number of steps is the same. And this is one thing that we need to talk about. How do you measure how good an algorithm is? Okay, so besides working and not working, and really we just want algorithms that work. The ones that don't work, let's not talk about them because they don't work. But for the ones that do work, might there be a time where, even though, like, let's say I have 2 search algorithms, that I would prefer one algorithm over the other? Like, how do I make that decision of which one of these things is better? Well, I'm seeing a question. Sorry, I just want to clarify. I thought -1 is an index. Okay. So, yeah, let me answer this one question real quick. So when I said, for example, this is index 0, 1, 2, 3, 4, and 5. And I was saying that if you don't find it, you can return, for example, -1, because that's not a valid index. In Python, which might be a language that you're familiar with, and I'm assuming that that's why this question was asked, you can use a -1 index. So if I said that, you know, this is my array, A, then, for example, A of 5 is equal to the number 18. But in Python, if you say -1, what that does is it imagines this array as sort of like a circle, or like a video game where if you walk off one end of the screen, you come in on the other side. Where a -1 would be go left, and then if you're now beyond the beginning, then wrap around and end up here. So in Python, you can refer to the very last element as -1. So that's, some programming languages work like that. I will not be taking that convention just for the ease of I don't know, some type of standard, I guess. So here, this does not exist in my world, okay, that I'm talking about arrays existing in. If you're working with Python, then you could return not a number, or you could return something else, whatever, like something that you could not return if it does exist. Like that's the point, that you're returning something that demonstrates that this thing isn't there. Okay. Let's see. I see some comments on how do you measure how good an algorithm is, how long it takes, which one is faster, speed. I see big O, that's a computer science term. Faster, how fast it works. Yeah, basically. I mean, this is, there's more ways than one, but this is a very common one. You can measure its speed. And prefer faster ones. Okay. Now, there's a question of how do you measure the speed of an algorithm? Let me pick on, how about, make sure there's no questions. Oh, use tests to see if it fails any. No. If it fails anything, then we're not considering it at all. It has to work. We're not going to take algorithms that work sometimes and not others. For a search algorithm, it has to work 100% of the time, always. What else did I see here? A success rate, how accurate it is. Again, it has to be 100% accurate. That's the bar. Like, there's no close enough things. No, it has to work 100% of the time. There are search algorithms that are correct with a certain probability and things like this, but this is 101 stuff. Okay, like nothing tricky or complicated. Okay. Oh, I see another question. Does it depend on space? This is another consideration that's very common for algorithms. How much space the algorithm takes. Space here meaning, like, if you're working on a particular kind of math problem, you might, be solving it on paper. Like if you're, I don't know, like 9 divided by 3, if you ever learn this sort of notation, that's the number 3. But if you have, like a really long number here, then there's a particular algorithm that you can follow, right? So this is the input. You're given a number and another number, and you want to know, does this evenly go into that or not? Or how many times does this go into that? Well, if you, I don't know what algorithm you guys learned in class or in school, but one common one is that you start all the way on the right, you see how many times I'm sorry, other way around. Yeah, you start at the beginning, see how many times this is evenly divisible, this is 3, and then you go to the next one, that's 7. I can go in 2 times into 7, and then you carry 1 over, So now you look at, how many times can 3 go into 10? That can go in 3 times, carry a 1, and like this. And you can go on and on and on. And if you're following this algorithm, you might, take up more and more and more space here on your sheet of paper to carry out all of the carries and whatever. So an algorithm can work the same way. It'll have a certain amount of working space. And sometimes an algorithm can run faster if you give it a lot of space. Or sometimes you don't have a lot of space to work with, so you choose a slower algorithm because you're limited in space. We'll focus on speed for now. Space is a consideration, but for now, let's focus on just speed. Okay, how do you measure the speed of an algorithm? Let me take this array so I don't have to keep writing it over and over. Paste it here. Perfect. Okay. How about Jeffrey? Do you have a mic? I think we only have one Jeffrey. Okay, how about Jerry?
Hello.
Okay, great. All right, thanks. Good to know, Jeffrey. I might come back to you. But
Professor,
yeah, yes,
can you just repeat the question one more time? I'm sorry.
sure. Oh, so I haven't even stated the question yet.
Okay.
So what I want to talk about is how do you measure the speed of an algorithm? So let's say if you're looking for the same as above, look for 3. How many steps does that take?
I think it takes about 4 steps because it will start from index 0 and then it would go all the way to index 3. So in order to measure the speed, well, I would measure how much length it has to go through. So probably set up like a variable that counts like that counts how much times or how much steps it takes, and then that technically count as the how fast it goes, I believe.
Okay, so here you would say that this algorithm takes time 4?
Yes, because it has to travel 4 indexes until it reaches 3.
Okay, so then what if you look for 1? How many steps?
Just 1 step, because it would just look at the first index 0 and then find number 1.
Okay. Now this algorithm, it's the same algorithm, right? I mean, the algorithm is just the process that you follow. Given an input, you follow these steps, and then you produce an output. You use the same algorithm for both of these, right?
Mm-hmm.
Okay. So which number is better? Is 1 more accurate? Is 4 more accurate? Do you average them? Like, I mean, if I, yeah, this, I mean, which one of these is right? Or is it not just one number? Is it something else?
I feel like it might just be something else because they're both accurate. Maybe my interpretation on measuring the speed is a little bit off then.
Okay,
Because I'm
yeah,
just putting it in, yeah.
good. Okay, so I'll just give you the answer. So you measure speed by the worst case. Okay, that's how you measure the speed of an algorithm. Imagine the worst thing that could possibly happen and measure the algorithm in that way. So here, what's the worst thing that can happen? What would make this algorithm take the longest amount of time?
I guess when it can't find the number that it's looking for.
Sure. Okay. Yeah, it can't find the number. And so then, yeah, what number is that then?
I would say total of 6.
Yeah, 6 or 7, whatever. Okay.
I mean 7 if you count the step afterwards, but yeah.
Yeah, because you got to fall off. Well, whatever. Sure. I mean, 6 or 7 doesn't matter. Like this kind of thing, +1, -1, whatever. Don't like fret over these things. Be it in a homework or test or whatever in this class. Like they don't matter. Okay. Now, a similar thing would be, what if I just had an 3 elements? I don't know, 20. Then if I measured the same algorithm, I would get a different number, right? First of all, you recognize this problem? I'll take that as a yes. So, what you do here, 3, is that you imagine a general array. A general array, or how can you make an array generalized, is you say that there's some index 0, and then it goes on for a while until the end. And whatever the end is, we'll call that number n. So in this array, n equals 3. That's the length of the array. In this array, n equals 6. And so we can say that linear search takes time n. Okay, so that is something to know. The linear search takes time n, where n is whatever the length of the array is. If the array is 100, then in the worst case, it could take up to 100 steps to come up with an answer. If the array is 1 billion, then it can take 1 billion steps, whatever. We'll just call the length of the array, we'll call it the number n, and then this way we can say that a linear search takes time n. Again, this is in the worst case, but that's the convention that we're using. There's also best case and average case and stuff like this. But again, like this is a standard thing to measure algorithms by their speed and to measure them in terms of the length of the input. Here, the length of the input is the size of the array, and so that's the number n, or the letter n. Oh, again, so here, is it n? Is it n minus 1? Is it n plus 1? That you don't need to worry about. Okay, this is, somebody else said big O. Big O notation, you would say it's written like this. So it's a big O, and then the running time. The reason why it's called big O is because it fudges the numbers. Okay, that means that each of these, O of n minus 1, O of n plus 1, all of these things are O of n. Okay, why? Because when you imagine n being very, 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 very big, then a plus 1 or a minus 1 isn't going to change anything. Like, you know, if n is some number with 100 digits, you add 1 to it, who cares? Like, I mean, you know, it's a 100-digit long freaking number. Like a plus 1 or a minus 1 isn't going to change anything. In the same way, let's say if you had O of n squared plus n plus 1. Here, you can also just call this O of n squared. Because again, if you imagine n being a really, 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 really big number, then this is going to dominate this. This is tiny, 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 compared to this. This is big. When the number n gets sufficiently large. Okay, so this is more of a formal way of writing. If you prefer, you can write the big O. I'm not asking or requiring you guys to write that. You can just say it takes time n. That's fine. Formally, this would be it takes time O of n, big O of n. But yeah, like this isn't a computer science course, so that's fine. Yeah, so I mean, I'm implicitly using the big O notation. I'm just not actually going through it. I think this has been maybe enough of an explanation. And if everything that I said here made no sense, don't worry about it. You can just forget it. In fact, I'm going to be erasing it from the notes. That's just for those who are curious. And also to know that, I mean, yeah, like on a homework or a test or whatever, I don't care about plus ones, minus ones, this kind of thing. Like, just forget about it. You can add it if you want. You can take it away if you want. I mean, I'm not going to care about it. I care about the big thing. Okay. So this is linear search. Let me write this up here. Linear search. Time n. Move this a little bit. Give myself some room. Okay. Now, there is... well, let me just ask openly. Besides a linear search, can you guys think of any other search algorithms? Binary. Nicholas, can you explain what this is? What's a binary search?
Yeah, so isn't when you basically take the average of the indexes, so you keep dividing the array in half, and then divide the halves into halves in order to find what you're looking for?
That's part of it, yeah. Can a binary search work on anything that a linear search can work on?
Well, I mean, it probably could, but it probably just makes it easier when you have a larger array.
Okay. So for example, let's try. I don't know, whatever. Okay. So find the number one. First of all, with a linear search, can you find the number one?
Yeah.
Okay. How many steps does that take?
5.
Okay. Great. And that takes 5 because you looked here 1, then here 2, then here 3, then here 4, and then here 5, you found it. Okay, so that's where that 5 comes from. Okay, how would a binary search work?
Well, I mean, I guess since it's like it doesn't divide the entire array evenly, couldn't it take like the like 1/2 with more elements of the array and then still divide that? Does that make sense?
Sure. So, I don't know. Let's make it like this then. There's 4 elements and then there's 3 elements. So, which way does the binary search go?
I don't know.
Okay, no problem. Okay, thank you. Afreen, I see you saying you should start in the middle. Okay, so we start at this index, we start at the middle index, and then what? Well, 2 is not equal to 1. So for a binary search. 2 is not equal to 1, so what do you do after that? Do you know? Okay, well, we'll get to it. It goes right. Why does it go right? And you can't say because I see the number 1 there. That's the way that humans work. It goes both ways. Yeah. Not quite. So here, well, I'll just give you the answer. A binary search doesn't work on this array. You can't use a binary search on this. Because a binary search only works in a sorted array. That's right, AJ. The array has to be sorted. And that's important because the binary search algorithm relies on that. Very quickly, when I was asking about other ideas that people had for searching, somebody said binary first, and then somebody else said reverse. A reverse search is also a linear search. I mean, it's just going, instead of from left to right, it goes from right to left. It still takes the same amount of time in the worst case, which is time n. Yeah, they're both considered a linear search. Okay. Now, the binary algorithm. Which type of search is faster? So it depends. Well, the quick answer is binary search. Binary search is faster. But the data needs to be sorted. And sorting takes time. So if you need to search and then, or I'm sorry, if you need to sort and then search, then the linear search is faster. But if you're given a sorted list, then the binary search is going to be much faster than the linear search. In general, you can just say that the binary search is faster. But there's also the caveat that the data has to be sorted. So let me sort this data, and I'll go through one binary search by myself, and then I'll go through another one with the student that I'll just pick at random. Unless you want to answer it, in which case, I don't know, type in the chat and I'll pick you. Or 13, 18, 42. Okay, so now we have a sorted list. The binary search, it's called binary for 2 reasons. Well, really it's 1 reason. At every step of the algorithm, it removes half of the remaining list. So it removes half of the list. And then from what remains of that, it eliminates half. And then again, it eliminates half. And then again, it eliminates half. And so because always you're taking the list and looking at it in two parts, one part of which you're just throwing out, that's why it's called binary, okay? Because it's you're splitting something in two, and you're always disregarding one half. So here, let's try to find the number 1. We start in the middle, okay? The binary search does. And 4 is not equal to 1. But now you ask yourself a question. Is 1 bigger than 4, or is it less than 4? Because 1 is less than 4, and because this list is sorted, and this is why it's important that it's sorted, that we know that if 1 is in this list, it's certainly not on the right side. We're looking for the number 1. We start in the middle of the list. 4 is not equal to 1, so we know we should move left or right. But because 1 is less than 4, if it exists, it'll be somewhere on the left-hand side of the list. Because 4 is bigger than 1, everything to the right of 4 is also bigger than 1. So there's no point in even looking at it, okay? You just throw those out whatever, you don't even have to look at them. Because you're guaranteed, because the list is sorted, that the thing that you're looking for, if it exists, isn't there. Okay, so now we go again to half of the list. Now we're at 2. And it's not that, because we were just there. 2 is not equal to 1. 1 is less than 2. Therefore, 1, if it exists, will be on the left-hand side. Certainly, you don't need to even bother looking at the right-hand side. And then you go again, and you know it's not that one, and now you find the number 1. So here, the binary search takes 3 steps. Granted, the linear search in this case would have returned faster than the binary search, but that's not the way we're measuring. We're not measuring on a specific example. Well, you always have to measure with the worst case. So this does happen to be the worst case for the binary search, when it's either the very first element or the very last element, or otherwise if the element doesn't exist. Okay. What would happen if the list isn't sorted? If the list is not sorted and you try to do a binary search, there's no guarantees that it will work at all. I mean, it could just return nonsense. Or it would very often say no when the element does in fact exist. So it wouldn't be a reliable algorithm anymore. So if the list is unsorted, then don't bother using a binary search. There's no guarantees of it working. In fact, it very likely won't work, like most of the time. Okay, great. Now, for the linear case, that's fairly straightforward. That it takes time n. That is, it takes time of the length of the list in the worst case. Because in the worst case, the thing that you're looking for is in the last place you look. And in the meantime, you've looked at every single thing in between. Okay? So for a list of length n, it takes n steps in the worst case. The worst case for a binary search is not time n, it's time log n. So here, a linear search, time n, a binary search is time log n. That's log base 2 of n. You don't have to write the base 2. You can if you want, don't have to. At least in this context, I mean, it's clear that it's the number 2. Okay, why does it take time log n? Log is log base 2 of some number is how many times you can break something in half until you can't break it in half anymore. Okay, let's see that quickly through some like simple examples. We'll start with an array of 2, and then we'll do an array of 4, and then an array of 8, and then an array of 16, and by then I'm sure you'll get the point. Okay, sorry, it's a bit long. Okay, so this is of length 2, length 4, length 8, and length 16. So how many times can we break each of these in half until we end up with just one element? So in this case, we break it in half once. You know, it's something that has 2 pieces. You break it in half, and now you've already got your 1. Okay, so that takes, you can, how many times to break in half? How many times to break in half until you have 1 cell? In this case, it's 1. Okay, you have 2 things, you break it in half, and you're already down to 1 thing. In the case of 4, well, you break it in half, right? So you have 4 things, break it in half, now you have 2 and 2. Throw one of them out, because that's what the binary search does, and now you have something of length 2, you break it in half again, and now you're left with single pieces. So this takes 2. Okay, so here, like, you break it in half, you throw this part away, and then here you break it in half again, and that's the 2. For 8, right, you break it in half, and you throw out 1 half. You have another half, you break that in half, and then you throw out half of it, and then you break it in half again, throw out, and now you're left with 1, so that takes 3. You can probably guess that's the number 4. Okay, if you have 16 things, you break it in half once, you have 8 and 8, throw one of them out, take the 8, break it, you have 4 and 4, throw it out, then 2 and 2, and then 2 becomes just 1 and 1. So 4 steps. Okay, so this is, if this is n, the length, n, then these are log n, log base 2 of n. What power do you need to raise 2 in order to recover the length? That's another way of thinking of it. Instead of breaking it in half, how many times do you break something in half until you end up with 1? You can ask the reverse question. How many times, starting with 1, do I have to double, until I reach the original length? Okay, that's the number of times starting from 1 you need to double something in order to get n is the same as if you begin with n and then you're breaking it in half again and again and again until you end up with 1, right? It's the same process, just going in 2 different directions. Okay, so that's what a log is. It's, yeah, in this case, the number of times you can break a list in half until you get an answer. Now, for those of you unaware, a logarithm is the other side of the coin of an exponent. So you know, like how, you know, you have addition, subtraction, right? Here you have addition, and the opposite of addition is subtraction. And then you have multiplication, and the opposite of that is division, right? They're the same thing, just going opposite ways. Here, if you take some number raised to some power, then the log of that is the opposite side. So an exponent is the other side of the coin of a logarithm. Okay. That is to say that log n is exponentially faster than a linear search, which is a lot faster. Okay, you don't quite see it here on these numbers, right? The number 16 compared to the number 4, not so different. But if you continue this, and now let's say you get to 2 to the 1,000, right? I mean, this is, sorry. 2, that's 2 to the 1. This is 2 squared. This is 2 cubed. This is 2 to the 4th, right? And because that's 2 to the 1, that's why that's the number 1. This is 2 squared. That's why that's the number 2, okay? Therefore, if you had a number like this, 2 to the 1,000, the logarithm of that is 1,000. So for a linear search on something this size, which, I don't know, let me see if I can, I don't even know if Google will work with that. Okay. So in decimal, I mean, this is 1.07 times 10 to the 301. Okay, so this is like a 300-digit number. Okay, it's a big number. All right, I don't even like that's. I don't know. It's like beyond a Google. It's a big number, right? I mean, 300 places. That's how long a linear search would take on something of this size. Versus a binary search that takes 1,000 steps. Right? In this case, like as the number n gets bigger and bigger and bigger and bigger, the difference between these two also becomes bigger and bigger. So a binary search here is much, much, much faster than a linear search. So why not always use a binary search then? If it's so much faster, then why not, why is the linear search even a thing? Why even talk about it? Again, it's because the data, the input for a binary search has to be sorted. If you have unsorted data, the best you can do is the linear search. Because things are unsorted, there's no smart, clever way to go through and find an element that you're looking for. In the worst case, that will be better than just looking everywhere. You could make that a formal argument. I won't. Again, this isn't a computer science class. But I'm just telling you that if data is unsorted, a linear search is about the only thing you can do. But if the data is sorted, then a binary search is exponentially faster. Okay, exponentially here, right? Because I mean this is an exponent, right? And now I'm just taking whatever the exponent is. So it's exponentially faster, which is to say, yeah, much, much faster. Okay. Yes. Now, so if a linear search takes time n, and binary search takes time log n. Sorting, to sort a list, takes time n log n. Okay, I'm not going to be going into a search algorithm, or I'm sorry, a sorting algorithm. If you're curious, merge sort can do this. There's others, but merge sort's an easier one to learn. I'm not going to be going over it. The point is that this is bigger than the number n. So if you only have to search one time and you have unsorted data, then just use a linear search. But if you're going to be searching again and again and again and again and again and again, like you're going to be searching many, many, many times, then waste a little bit of time in the beginning, and this will be a recurring theme in this course. If you take a little bit of time in the beginning and kind of waste it to take an unsorted list and then sort it, the benefit that you get is that now you can do a binary search. So if the main thing that you're doing is searching, then go ahead and eat the upfront cost of sorting, and then you can use your fast search. If you only need to search like once or twice, don't bother with sorting because it takes too long. But that's the trade-off. Okay. Any questions before we end the lecture? Okay, in that case, I hope you guys have a good rest of your week, and I will see you on Monday. I see a question. Sorry, when do you sort again? So you sort at the very beginning. That's the first thing you do. So if you're given unsorted data, and you want to use a binary search because you're planning on searching many, many, many times, then you get the unsorted data, and then you spend a lot of time sorting it. And that takes n log n time. Whatever, it takes time to sort. But after you've done that now you have a sorted list. And so you can just use the binary search. So that would be the steps of the process. If you're planning on searching a lot. If you get unsorted data, sort it, and then do the binary search.
Professor?
Yeah.
I just have a quick question. So, is it easier to directly use the linear search, or is it easier to like first sort the unsorted list and then use the binary search? I feel like, wouldn't that take more time if we're like sorting it and then using it?
Yes, it does, but it depends on how often you're planning on searching.
Mm-hmm.
So,
Okay.
because it takes time n log n to sort, then you could say, I mean, if you're planning on doing at least n log n searches, then it's worth it to, in fact, no, even worse than that. If you plan to do log n searches, then it's worth it to sort your data first and use binary search. Why?
Okay.
Because if you're searching for something log n times and you're using a linear search, each one of those times is going to take time n. So the total amount will be log n times this is the speed of the algorithm, and this is the number of searches. So now you've already used n log n time. So if you're planning on doing more than that, in this case, if you had this much data, and you were planning on searching at least 1,000 times, then then you're beneficial to sort first and then use binary search. Yeah.
Thank you.
Mhm. Yep.
Hi, Professor.
Yeah.
Why did you specify merge sort instead of like a insertion or selection sort?
Oh, like I said, I mean, there's many different types of sorting algorithms. I just chose merge sort because it's an example of one that does this in time n log n, which is the best that any algorithm can do on sorting data, unless there's some other qualities about it. Like if it's mostly sorted, then you might be able to do you might be able to finish sorting it faster than n log n. But if there's no guarantees about anything of the input other than it's unsorted, the fastest that you can do is n log n, and merge sort is just an example of that. It's one algorithm that does it.
Okay, gotcha,
Yeah.
gotcha. Thank you so much.
Yeah. If you know others, that's fine too. I was just giving an example for students who are interested, I guess. But I don't expect people to know that for this course.
Yeah, because I've learned insertion and selection, just never heard of merge sort. That's why I was asking.
Okay, yeah. Merge sort of it's pretty easy. I mean, it basically you take your unsorted list and then you break it in half, break it in half, break it in half. So you have all these different halves until you get down to single elements, and then you just compare those two elements. And then if one's bigger than the other, you swap them. So now you have half of your data in units of 2, each of which these 2 units are sorted. And then you take each of these 2 units and then you put them together in a unit of 4,
Compare.
of length 4, and then sort those. And then you do it then you take your ones of length 4, merge them to be of length 8, then from length 8 to, and like this. And so it takes log n many times to break things down to single units. And then there's n comparisons that you're doing, and then merging back up is another log n. It's not exactly n log n steps, but it's of that order. It's big O n log n. Like n log n plus some other stuff. Or maybe it's like, 2 n log n, but that's still just n log n.
Gotcha. Thank you.
Yeah.
Have a great day.
Yeah, you too. Okay. Okay, great. All right, well, I'll see you.